Hello all, welcome back to our channel Complete Chemistry. Today we are going to see about molecular orbital theory or molecular orbital energy diagram of oxygen and fluorine. In our last video we have seen about molecular orbital theory and also molecular orbital diagram of nitrogen. So today we will be seeing about oxygen and fluorine. We'll just go to whiteboard and then see what is it. So, while drawing your molecular orbital energy level diagram of oxygen, what are the important points that we need to look into, or what are the important points that we need to consider and write in our exams? Our first point that is important here is your atomic number of oxygen. First point is, what is atomic number of oxygen? Atomic number of oxygen is 8. What is atomic configuration? Electronic configuration of oxygen. Electronic configuration is 1s2, 2s2, 2p4. Right? Now what is the next point here is your oxygen. 2 oxygen atoms combine to form your molecule O2. Now oxygen atom, one oxygen atom will have 8 electrons and the other oxygen atom will have 8 electrons. It will combine to give out 16 electrons are involved in your molecule formation, oxygen molecule formation, right? Now we'll see how are these entering into orbitals, molecular orbitals. So this is our energy level diagram that is present, and here we need to write that is your energy is increasing. This is very important while you write your exam theory part, right? Now what are this side and this side are your atomic orbital of your oxygen this side and your atomic orbital of oxygen to the other side. Now what is at the center in this part is your molecular orbital of oxygen. All this center part will be of molecular orbital of oxygen, right? Now this first thing is your 1s orbital. First 1s orbital is considered and we are going to draw it like this, and then coming to your second 2s orbital, these two are of atomic orbitals, right? And then coming to your third level, that is your 2p orbital, you have 3 p orbitals, px, py and pz, and even here also we are going to represent the same thing, 3 p orbitals, px, py and pz. Now we'll start filling up of your electrons. 1s2, 2s2, 2p4 of one oxygen atom we are going to fill up in your electrons here, like 1s2, 2 electrons are filled up here, 2s2, right, 2 electrons, 2p4, 1, 2, 3 and then 4. Now filling up of these electrons in molecular orbital energy level diagram also follows Hund's rule, Haber principle and Pauli's exclusion principle. Your filling up of electron takes place, like pairing up of electron takes place only after it is half filled, right? Even in this side we are going to fill up your electrons, right? 1s2, 2s2, 2p4. Fourth electron will be paired up with the first electron. Now coming to your molecular orbital energy level diagram, as I said you, if 2 atomic orbitals are involved, then it will form your 2 molecular orbitals in case of your molecular orbital theory. Now here are your 2 atomic orbitals, so it is forming 2 molecular orbitals. These 2 are your molecular orbitals. One is your bonding molecular orbital and the other one is your anti-bonding molecular orbital. Bonding molecular orbital will be every time lower in energy and the stable one. Anti-bonding molecular orbital will be higher in energy and unstable one. Bonding molecular orbitals are represented with sigma and pi, whereas antibonding molecular orbitals are represented as sigma star and pi star. Now here coming to this level, it is 1s orbital that is involved, so we will be writing it as sigma 1s, and here it is sigma star 1s, and here it is sigma 2s, and here it will be sigma star 2s. Now coming to this area, first we'll fill up these two orbitals and then we'll go to the 2p orbital, right? Now here what happens here, how we will be filling up your electrons? 4 electrons are present, 1, 2, 3 and 4 electrons are present. First 2 electrons will enter into bonding molecular orbital and then next 2 electrons will be entering into anti-bonding molecular orbital. So 4 electrons are filled up in this way, right? In the second level also, 2s level also, 4 electrons will be filled up, 1, 2, 3 and 4 electrons are filled up, in 2 in bonding molecular orbitals and 2 in anti-bonding molecular orbitals, right? And now coming to your this 2p level, which is very important and which differs from your nitrogen. Nitrogen we have different diagram, and here oxygen and fluorine will have different diagram, right? Now what is going to be at the down energy level or lowest stable energy level, and what is in the upper stable energy level? Now let us take this oxygen. One atom, we are more concerned about your valence electrons. Valence electrons are the outermost orbital electrons, right? And now we'll just take about your p orbital, where you have px, py and pz orbitals. As I said you in the last video, that your pz orbital will be forming up your sigma bond because of its head-on overlap, whereas px and py will form your sidewise overlap and thereby forms pi orbital. So here 1, 2, 3, 4 electrons are present. 1, 2, 3, 4 electrons are present. So bonding electrons that are involved in bond are these two py and pz orbitals, right? Now as this is forming one bond, and this also will form one more bond, right? Now pz orbital, as I said, it will form sigma bond, and the py will form your pi bond. Now, as I said in your nitrogen case, as more number of pi bonds are present, and it's a half-filled electronic configuration, pi molecular orbitals will be coming down, will be lower in energy than your sigma bond. But here, one sigma bond is formed and one pi bond is formed, so they are equally shared, and when equally shared, we are going to consider which is the stable bond. Now coming to the stable bond, it is your sigma bond that is most stable than your pi bond. So coming here you will have your sigma bond, that is your 2pz orbital, sigma 2pz orbital, and here you have your pi orbitals, pi 2px and pi 2py orbital. And same way you will have, in the same way, there will be no change in case of your anti-bonding molecular orbital, that is your pi star 2px and pi star 2py in the lower energy level, and sigma star 2px on the upper energy level, 2pz in the upper energy level. Now when you start filling up your electrons here, 8 electrons are present, 4 electrons here and 4 electrons here. Now coming to this, 2 electrons are filled up first in your bonding molecular orbital, that is your sigma 2pz electron, and then third electron enters into 2px, fourth electron enters into 2py, and fifth electron will pair up here. Then complete electronic configuration is here. 6 electrons are filled up in your bonding molecular orbital, whereas 2 more electrons are left out, and those 2 more electrons will enter into anti-bonding molecular orbital. Your 7th electron enters into pi star 2px and 8th electron enters into pi star 2py. Now here this is your configuration, the uppermost electronic configuration here is unpaired, right? This is your molecular electronic configuration. So fourth point here will be configuration, molecular configuration of your oxygen, molecular configuration of your oxygen. How will we write now? We'll start from sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, sigma 2p pi 2px2, pi 2py2, pi star 2px1, this is 1 because only one electron is present, and pi star 2py1. Yes, now we'll start writing it here. Sigma 1s2 is greater than, because the energy here is lower in energy, and most stable one, I am writing it as stability. According to stability, I am writing it here, is most stable than your sigma star 1s2, right? And this is most stable than your sigma 2s2. Then this is most stable than your sigma star 2s2, right? And then comes your sigma 2pz2, and then comes your pi 2px1, because only 2px2, and equal to, we are writing it as equal to symbol because these two orbitals are present on the same energy level, right? So there will be both the orbitals will have stable same stability. Then we have your pi 2p y2, and then continue. I'm continuing here. It is greater than, like stability is more than your pi star 2p x1. Here it is 1, and then it is equal to pi star 2p y1. Right? So this is about your molecular configuration of your oxygen. Then the fifth important point that we need to write about here is your bond order. What is your bond order? As I said you, this is half the difference between your number of bonding electrons and anti-bonding electrons. Bonding electrons are those in where electrons that are present in bonding molecular orbitals, like this is your bonding molecular orbital, this is your bonding molecular orbital, and all these are your bonding molecular orbitals, are called as your bonding electrons. And antibonding electrons are those where your electrons present in your antibonding molecular orbitals. This is your antibonding molecular orbital, this is your antibonding molecular orbital, and these are your antibonding molecular orbitals. So the electrons here are called as your antibonding electrons. Now coming to the number of count, like half into number of bonding electrons. See, here we can cancel off these bonding electrons because both are same, and here also we can cancel off bonding electrons. Now we are most concerned about only p. Now number of bonding electrons here are 1, 2, 3, 4, 5 and 6 bonding electrons that are present in bonding molecular orbital. So we'll just write it as 6 here. And minus antibonding electrons here are 1 and 2 electrons. 2 electrons are present, so 2. So what you get here is half into 4, you get it as 2. It means that oxygen atom is bonded with one more oxygen atom with a double bond. Of these two double bonds, one will be sigma bond and the other one will be pi bond. One will be sigma bond and one pi bond. Right? And the next important point that we need to see about here is your stability. As I said, stability depends upon number of bonding electrons and number of anti-bonding electrons. If number of bonding electrons are more than your anti-bonding electrons, then the molecule is said to be stable one. Right? And now here number of bonding electrons here are 6 number of bonding electrons, and anti-bonding electrons are 2. So bonding electrons are more than your anti-bonding electrons, so oxygen molecule is said to be a stable one. Right? And the seventh important point here is your magnetic nature. Seventh important point here is magnetic nature. Magnetic nature here depends upon the highest electronic configuration of your molecular orbital diagram. What is the highest electronic configuration here is this one, 2p y1, right? And see, this is unpaired electronic configuration is present here. As unpaired electronic configuration is present in the molecular orbital diagram, we say this oxygen molecule, unpaired electrons are present, we say this oxygen molecule is paramagnetic in nature. If it is a paired up electronic configuration, then we say that that molecule will be exhibiting a diamagnetic nature, like that of your nitrogen, and fluorine will exhibit diamagnetic nature. But oxygen here is paramagnetic in nature. So when you are going to write about your oxygen, you need to write about all these points. Very important, right? Then we'll see about your fluorine. Fluorine electronic configuration for fluorine atomic number will be 9. Yes, fluorine atomic number will be 9. Start from the first point, as I've said you can do it, right? If you can do it, please pause my video and then start doing it and check it whether you have written correctly or not at the end. Atomic number of fluorine is 9. Atomic configuration or electronic configuration. What will be the electronic configuration here? It is 1s2, 2s2, 2p 4, and this will be your 2p5, right? And what is the third point that we need to see? Fluorine plus fluorine will give you a molecule of F2, right? Fluorine here 9 electrons plus your 9 electrons. Most total involved electrons are your 18 electrons in your molecule, right? Now we'll start filling up your electrons. This is your atomic orbital of your fluorine, and this is your atomic orbital of your fluorine atom. And coming to this will be your molecular orbital of your F2, right? This is your 1s, this is your 1s, this is your 2s, 2s, 2p here and 2p here, right? Now when you start filling up of your electrons, 2 electrons over here and 2s2, again 2 electrons, and then coming to this, it is of 5 electrons, 1, 2, 3, and then 4 and 5 electrons here. In the same way, we will be filling up here also 2 electrons, 1s2, 2s2, 2 electrons, and then here 5 electrons in all the 3 atomic orbitals of your p, right, 2p5, right? Now coming to this bonding molecular orbital, as I said you, this will be sigma 1s, and you are going to fill up your 2 electrons here and 2 electrons in case of your antibonding molecular orbital also. This is your sigma star 1s2, and this is sigma 1s2. And then coming to your this sigma 2s2, where you 2 electrons, 4 electrons are present here, so 2 electrons will be going into bonding molecular orbital, and the other 2 electrons will be going into sigma star 2s antibonding molecular orbital. And then coming to this, as I said you, here only one sigma bond is forming, right? Only one sigma bond will form, so sigma electrons will be coming, sigma molecular orbital will be coming down, sigma 2pz, right? And here you will have your pi electrons. This is your pi 2px, and this is your pi 2py. Now how will you fill up your electrons? This is your pi star 2px, and this is your pi star 2py. We are not going to change anything in this antibonding molecular orbital, so this is your pi star 2pz, right? Now start filling up in your p orbital here. 10 electrons are present totally, so 1, we'll just change pen here. So 1 electron, 2 electron, second electron, third electron enters into 2px, fourth electron enters into 2py, and fifth electron into 2px, sixth electron into 2py, seventh electron enters into antibonding molecular orbital pi star 2px, eighth electron enters into pi star 2py, ninth electron starts pairing up your pi star 2px, and 10th electron pairs up with pi star 2py. Right, this is your electronic configuration that we have. And the fourth point here is you need to write about molecular configuration. That is, how will you write your molecular configuration? I am writing about writing according to stability, right? Now if you are writing according to your energy, then your sigma 1s 2 will be less than your sigma star 1s2. If you are writing according to energy, lesser than symbol will come, because sigma 1s2 is of lower energy than your sigma star 1s2. Then coming to this, you just mention it whether you are writing it with respect to energy or stability, right? If it is energy, this is the one. Then sigma 2s2, then comes your sigma star 2s2, because this is after sigma 2s2 you get your sigma star 2s2. Then comes your sigma 2pz2, right? Then sigma 2pz2, and then which is lesser than your pi 2px2. Here also 2 electrons are filled up, so pi 2px2, which is equal to, because these two are present in the same energy level, these two orbitals are degenerate. Itself means same energy is present among them, and stability also is same. So this is your pi, I'll just write it here, pi 2py2, which is less than your pi star 2px2, and this is equals to pi star 2py2. So this is your molecular configuration of your fluorine. Coming to your bond order of your fluorine, how will you write your bond order? Bond order is equal to half into number of bonding electrons minus number of anti-bonding electrons, right? How many bonding electrons are present here? Now we'll just cancel off these two and these two will get cancelled. Now you're concerned about these bonding molecular orbital electrons, that is your bonding electrons, and these are anti-bonding molecular orbitals, that is anti-bonding electrons. Now how many bonding electrons are present? 6 bonding electrons are present. 1, 2, 3, 4, 5, 6 electrons minus anti-bonding electrons 1, 2, 3, 4 electrons. So we'll just write it here. So what is the thing that you get here is 1. It means that fluorine is bonded with one more fluorine with a single bond, that is your sigma bond, right? Now coming to the next point is your stability. Stability is again decided by number of bonding electrons and anti-bonding electrons, number of anti-bonding electrons. If number of bonding electrons are more than number of anti-bonding electrons, then the molecule is said to be stable. Now here bonding electrons are 6 and anti-bonding electrons are 4. So your F2 molecule is said to be stable, is a stable one, right? Then the seventh one here is magnetic nature. Magnetic nature, as I've said you, it depends upon the highest electronic configuration or the energy configuration. See here the electronic configuration here is paired up. See here, the last electronic configuration here is paired up 2. So we say that diamagnetic in nature. Your fluorine is diamagnetic in nature because of the paired up electronic configuration. So this is what I want to say today. So whenever you write about your fluorine or nitrogen or oxygen, the only difference that comes between your nitrogen and oxygen fluorine is in this part, only this part. For your nitrogen, your pi electron pi to px and pi to py will be coming down in the lower energy level than your sigma to pz, whereas in case of oxygen and fluorine, your sigma to pz will be coming down in the lower energy level and pi to px and pi to py will be coming on higher energy level. So this is the difference between your nitrogen and your oxygen and fluorine. Oxygen and fluorine will have same, only filling up of electrons is different, right? This is what I want to say, and these are the important points that are present when you want to write about your fluorine. So thanks for watching my channel Complete Chemistry. Keep watching for still many more videos on chemistry. Thanks for watching. Please like, share and subscribe. Give a big thumbs up if you like it and share it with your friends. Thank you.